All right, so circuit kit for series. Feel free to chime in as you have questions. What's up?
Oh, real quick, do you have any spare alligator heads?
I do not.
Oh.
Make the best of it. I know it's loosey-goosey, but try to figure it out. So here we have our multimeter. The multimeter measures voltage over here on the V side, and it measures current over here on the A side. We have our battery pack, and the battery pack, a lot of people are tempted to hook into this red wire, but if you notice that red wire just terminates here and doesn't go anywhere, so that's a rip. What we're going to do is we're going to attach one lead here because it's connected to all of this metal, which makes its way over to this black wire right here. All right, I'm going to grab my circuit kit, and I'm going to attach an alligator here. These are the alligators because they look like alligators. And alligator over here. And now I have my voltage source. I'm going to put that at the bottom of our screen there just to kind of keep everything laid out and organized here. Now, we're going to do one bulb, and if we hook a bulb up and it lights, then we did so correctly. So for current to flow, you need a closed loop, and indeed we have a completed loop and the bulb lights up. Now, if you look at your data table, we got to measure some stuff. So first thing is to do voltage, you go over here to the voltage side, and your plug arrangement should look like this. And to measure voltage in a circuit, all you have to do is touch the black lead to one side of the bulb and the red lead to the other side of the bulb. Now, it says 3.83 if you look pretty carefully. Not sure how tight the video is coming through there. But you can write that down for your first table. It's 3.83 volts for our single bulb. This also just so happens to be, if we touch this over here to the two leads coming directly out of the battery, about the same, 3.81, 3.82, so it's about 3.83. What you notice is the battery voltage and the bulb voltage are the same. That's because there's only one bulb, and the one bulb gets all the voltage. All right. The other thing we have to do is measure current. So I flip over here, move this up. You notice that it's saying A is 10, and so my plug has to be there. And to measure current, you actually have to break the circuit like this, so you see the bulb turns off, and then you have to arrange your multimeter in a position where the current must flow through that multimeter. So I'm going to lay it out like this for you. You notice the current comes out of the batteries, into the multimeter, into the bulb, and then back to the other side of the batteries. And if we arrange it correctly, we'll see this current. So right now, our current is measuring as 0.19 amperes. So you can write that down in your data table, 0.19, 0.2, hovering around there. We'll call it 0.19 amperes. That would be the current at bulb 1. So to measure current, you got to break the circuit. To measure current, you got to break the circuit because we need the charges to actually flow through that ammeter. Let's move these out of the way. And I'm going to rearrange my circuit so it's like this, just so you can see the shape of what's about to happen. For series, there's only one path, right? So we're going to say we got to go into this bulb. So battery pack comes over here. Let me make sure you can see all the wires here. Comes over here into this bulb, and we're going to jump over to this next bulb in such a fashion so that there's only one path for these charges to take. And when we plug them in, we notice this bulb is on, but this bulb appears to be off. Now, the reason I say it appears to be off is because it does have current flowing through it. If it didn't, the other bulb would also turn off. Okay, but this is our series circuit with a single path here. So let's take our measurements real quick for this. Again, with the voltmeter, all you have to do is touch the black to one side and the red to the other, like so. Oh, try again. Oh, I'm on the wrong lead here. Let's switch to the correct leads. Still no bueno. What's going on here? Oh, silly Simpkins. I bypassed the bulb. Let's try that. There we go. All right, what's up?
We have a cringe light bulb.
There we go. We are on circuit number 2. So here we have voltage. We're going to touch to this element, and we see over here we have 3.56 volts. So you can jot that for bulb 1 is 3.56 volts. Now take note, this bulb is the one that's lit up, 3.56 volts. It has most of the voltage. This one over here only has 0.38 volts. 0.38 volts for bulb 2. And if we do a check over here at our battery, we see 3.9 volts. 3.9 at the battery. So we have 3.36 over here, another 0.39 over here, and that the voltages should add up to the total voltage if Kirchhoff's loop rule is in action here. Now, although the bulbs have different voltages, and we can see that represented by one being brighter than the other, the interesting thing about a series is that the current is the same everywhere. Now again, to measure current in a series, you actually have to break the circuit and make the charge flow through the ammeter. And if I do that, I'm getting a measurement of 0.23 amperes. So you can write that down on your data table for bulb 1, 0.23 amperes. Now, you may say to yourself, well, Mr. Simpkins, that's the bright one, 0.23. I'll bet this guy doesn't have as much current. I'll bet this guy has a little bit less current, maybe. Well, it turns out, actually, that if I measure this and the bulbs come back on, I get the exact same number, 0.24 amps, or 0.23. There's going to be a slight variation, probably just because of the sensitivity of this materials. So what we see here is that the current going through both bulbs, and indeed even both through the battery, has to be the same. And this makes a lot of sense because we have a single path. If you have a really slow driver going down a single lane road and no one can pass them, everybody has to go the same speed. So that's why current is the same everywhere in a series circuit. Let's see if we can get lucky with 3 functioning bulbs here. I'll add one more bulb to our chain, or our series of bulbs. Throw this guy in here, like so. And these bulbs are the wires are a little extra long, aren't they? But you see here, if you follow it around, we come out of the battery, we go into bulb number 1, into bulb number 2, into bulb number 3, and back around to the battery pack. So a series, again, is like a link. It's like a daisy chain. It's one through each element to the next one, and you must pass through all elements to complete the loop. So let's take our voltage measurements for each component. We'll start with bulb number 1. Bulb number 1 is reading as 0.34 volts. Bulb number 2 is reading as 2.93 volts. 2.93 volts. And bulb number 3 is measuring as 0.25 volts. Bulb 3, 0.25 volts. We expect that in a series, this voltages should add up to the total bulb voltage. So again, the bulb voltage here is 3.86 volts. Bulb voltage, 3.86 volts. So that's for voltage. The last thing we need to do is current. Now, I'm going to kind of cheat a little bit because I think we've pretty well established that the current is the same everywhere in a series. So I really only have to measure it for one place, and it'll be the same number as I measure it in all the other places. So, again, to measure current, you have to disconnect the circuit, force the current to flow through the ammeter, and in this case we have 0.19 amperes of current. That's 0.19 amperes of current. And that amount of current is going to be the same all throughout the circuit because there is only one path. So at this time, what I'd like you to do is take a look at your data that we've measured in the first 2 columns and calculate the resistances and powers for the next 2 columns for those 3 circuits. And then we did our summary here, but make sure your summary matches up with the properties that we expect for series and parallel.